So today we'll be talking about bottom-up parsing. So far we did top-down parsing. So in top-down parsing, we start with the start variable, which is the root of the tree, and we work our way down the tree until we get to the leaves. And the leaves of the tree are what? The terminals. So in top-down parsing, this is top-down. We start with the root, which is the start variable, and then we keep making substitutions or expansions. In fact, our substitutions in top-down are, we call them expansions because they increase the number of symbols. So typically, you substitute S, AB, or maybe ABC. So most of the substitutions that you are making when you are going down the tree are going to be expansions. You are increasing the number of symbols until you get to the leaves of the tree, and the leaves are the actual terminals. So this is the actual string. So this is top-down. Now bottom-up, which is what we are about to describe, goes in the other direction. So you start with the terminals, you start with the string, and you work your way up the tree until you get to the root of the tree. So we go up. So our substitutions, when we are doing bottom-up, when we do bottom-up parsing, our substitutions are going to be reductions. So here, substitutions are expansions. We expand. But here we reduce. Why? Because we start with a large number of symbols, which is the terminals, and then we keep making substitutions that will reduce the number of symbols until we end up with the start symbol, which is just one symbol at the root of the tree. So we start from the leaves where we have a large number of symbols, and we keep doing reductions. These reductions are just substituting. If you have a grammar, if you have a production like this, and you have ABC, you substitute S for ABC. Okay. And in general, as we will see, generally speaking, bottom-up parsing is more powerful than top-down parsing. Why? Because as we will see, it will have access to both the left context and the right context. So let's take a concrete example. By the way, bottom-up, thinking bottom-up has been used to come up with more advanced techniques. For example, scientific methodology, you can think of it as a combination of top-down and bottom-up, because before people before scientific methodology, the scientific methodology that we know before it was introduced, many people did not believe in experiment. So when you think about experiments and conducting experiments and looking at the results of an experiment, then you are looking at concrete data. And when you make a generalization based on observations or based on the results of an experiment, you are going up. You are going bottom up when you generalize. You go from the concrete to the abstract. This is exactly what we do in bottom-up parsing. We start with the concrete, which is the leaves that have the actual string, and we go all the way up to the abstract, and the abstract is the start variable of the derivation. So we go from the concrete to the abstract. So scientific methodology is an example. democracy is another example. In democracy, it's things go when the people elect the president. This is bottom up, right? So and before that, before the introduction of democracy, everything was top down. But when people started to believe in democracy and implement democratic systems, the people or the leaves of the tree, select the president, and it's directly or indirectly. Whether you select delegates or representatives that select the president, whether it's direct or indirect. So you are going bottom up. Now in algorithms, how many people have taken 140? Okay, 140, the algorithms course, only 2 people? So one of you has to answer this question then. Okay, so which algorithmic technique uses bottom-up thinking? What's the powerful algorithmic technique that is based on using bottom-up thinking?
Is it dynamic programming?
Yeah, exactly. It's dynamic programming. So in dynamic programming, we use bottom-up thinking. We build solutions to the sub-problems, and we use solutions to the sub-problems to build solutions to bigger problems. And we keep building bigger solutions to bigger and bigger problems until we build a solution to the complete problem. This is as opposed to what? What's the other technique that does the opposite?
Don't remember.
Divide and conquer.
Yeah, divide and conquer, exactly. So divide and conquer does the opposite. Divide and conquer starts with a big problem and it divides a big problem into smaller problems. So when you do divide and conquer, you are thinking top down, and when you are doing dynamic programming, you are thinking bottom up. So, and in parsing, we'll see how bottom up thinking can be can lead to a more powerful parsing technique. Let's look at this example. The A is ABC or B, and B goes to D. So let's number the rules: 0, 1, 2, 3. So here we are numbering our rules. So A has 2 rules, rule number 1 and rule number 2. We are numbering the rules or the productions. And let's parse this string. A, B, B, C, D, E. Now, first of all, is this grammar LL1? No, it's not LL1.
It's the left recursion on A.
Yeah, so there is a left recursion on A. So this is not an LL1 grammar. So let's try to see how bottom-up parsing works on this. How we can parse bottom-up. Parsing bottom-up means you start with the string, and then you try to find a rule in the grammar that you can use for making a reduction. So you do the substitution. You substitute the right-hand side for the left-hand side. So in this case, you look at the A. Okay. So the A, you cannot do anything without reading the A. So we'll read the A. So now after reading the A, can we find the A somewhere on the right-hand side at the end of a right-hand side of a rule? So this is a rule. This rule ends with C. This rule ends with B. This ends with D. And this ends with E. So A never appears at the end of a rule. So we know that we cannot make a reduction with an A, because there is no rule that ends with an A. So when we can't make a reduction, when we can't reduce, we shift. So this bottom-up parsing technique is based on shifting or reducing. So we look for a reduction. We're looking for a reduction. If we can't find a reduction, we shift. And shifting means looking at the next symbol in the input. So now we shift. So now we have A and B. Both of them are are red, and the next symbol is a B. Now, is there a symbol? Is there a reduction in the grammar, or is there a rule in the grammar that ends with a B? Yeah. So there is one that ends with a B, which is this. So this is the only rule that ends with a B. Is there a rule that ends with the suffix AB?
Nope.
No, there is no rule. So in this case, this is the only option that we have, which is reducing the B into an A. So what we do is this. Our string now is A, B, C, D, E. And we are looking at the B. Okay. So now, this is what we have read. What is to the left of this pointer is what we have read. And which symbol is our look ahead? B. This is our look ahead. Now, we look at the rules. Is there a rule that ends with an A? With this A? No, there is no rule that ends with this A. So we don't seem to have an opportunity for a reduction. So we shift again. So by shifting, we just move. We read one more symbol from the input. And now we have AB. Now, is there a rule that ends with a B? Yeah. So this ends with a B. But now, there is a rule that ends with a B. But is B a good reduction to make? Is it a good idea to reduce B to an A here?
No.
Based on what?
Because
Yeah, one person. Yes, please.
because there was another character C, which does match the end of rule number 1.
OK, so if it matches rule number 1, what does this mean? In fact, what we care about here is whether it will be a valid reduction to reduce B to an A. If what can answer the question is asking whether C is what? Whether our C, the look ahead, whether it's what? Under what condition will this be a valid reduction? Given the look ahead and given what we have. So based on the look ahead, yeah.
If we have another option for reducing the C as is.
Well, reducing the C.
We don't have that though.
Okay. We are not looking at this other rule. This other rule is still we haven't read enough to consider this rule. Okay. Let's focus on deciding whether this reduction is valid or not. Whether substituting a B for an A is valid or not.
Valid.
Well, given the look ahead. So if we substitute it if we do this, A, C, okay. Does C ever appear in the follow set of A? So what's the follow of A here?
It's B and
So A here is followed by a big B, which is a D,
and
or a small b, right? Yeah.
yeah.
So this is about what we have in the follow set of A. So since the look ahead is not in the follow set of A, then this reduction will not be a valid reduction at this point, right? So we made this decision based on both the look ahead, which is what we have to the right of the pointer, and the left context as well. So based on looking at the left context and the right context, which is only one symbol look ahead, we were able to determine that a reduction here is not valid. It's not a good idea. So when a reduction is not valid, what do? We shift again. We do another shift. When we can't reduce, we shift. Okay? So now, we have ABC. So we look for a rule in which the right-hand side ends with a C. And the only rule in which the right-hand side ends with C is this rule. Right? And in this rule, we will be reducing this whole thing to an A by rule number 1. So we say that we reduce by rule number 1. Our first reduction was using rule number 2, right? So the first reduction used rule number 2. Now we will be reducing by rule number 1. So we will do A. And by rule number 1 says that you can reduce ABC into an A. And this is our A. And now we're almost done now. Because now we are looking at the D. Again, we look at what we have on the left-hand side of the pointer, which in fact will be in the Lr1 parsing will be placed in a stack. So this is the stack. This will be the stack that has what we have consumed. And what we have to the right of the pointer are the symbols in the input string that we have not consumed yet. So what we consume, we push it on a stack. So in this case, our stack will look like this. Well, for this, our stack, we don't have a specific here. So the stack will have an A, then an A at the top. This is our stack at this point. This is our stack, what we have read. And the D is our look ahead. Now, we don't have anything that ends with A, which means that we cannot reduce A to something else, the big A. Because you can make multiple reductions. Reduction is not that you only make one reduction and you can make a sequence of reductions. Now, given this, I have to shift. So I shift. Now I have a D. Do I have a rule that ends with a D? Yes, I do. Obviously this. So now I can reduce. So I do A, B, and E. And now, sorry, I still, I'm not there yet. So B and E. OK, I don't have a rule that ends with a B. So this is going to be my stack, in fact, at this point. So I cannot reduce because there is no rule that ends with a B, a big B. OK, so I shift. And now I have the E on the stack. So E is on the top of the stack. So do I have a rule that ends with E? Yes, we have this rule. So this rule tells me that I can reduce this whole thing to an S. So now I have an S. So this is the top-down parsing. These are the leaves of the tree, and this is the root of the tree. So these are the leaves. Or let me write it in blue. Leaves, and this is the root of the tree. Okay. So this is just of course, we haven't shown yet, we haven't described the actual algorithm for doing Lr1 parsing, but this is just to give you an idea that we start with the leaves, which is the input string, and we keep making reductions until we end up with the start variable. Okay, and we make our decisions to shift or reduce based on the left context, which is what we have consumed, and the right context, which is limited to one symbol, look ahead, which is the look ahead, the next symbol. Okay, so now let's see how we can apply this to the classic expression grammar. So we'll write the classic expression grammar. Expression is expression plus term, or expression minus term, or term, and term is factor is term times factor, or term divided by factor, or factor, and factor is number, or identifier, or expression. And since since this rule has multiple alternatives, we would like to have a start variable that doesn't have multiple alternatives. So we just introduce one start variable goal that we give it expression. Okay. Okay. So we number the rules. This is number 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 rules. And let's see how we can parse the string. So our string is going to be just the string that we used in previous lectures. X plus 5 times y. X plus 5 times y, which is an identifier, plus number times identifier. Or let's just, for short, let's say ID. So let's say how we can use this. So this is our stack, which is initially empty. This is the input, and this is the action. Okay. And we will have many steps in parsing this string. Okay. All right, so now our stack will initially be empty. And our input is going to be an ID plus number times ID. Okay, so what should our first action be? Shift or reduce? We haven't read anything, so we first shift. We first shift. Shifting means that you are pointing here. So shifting means consume the ID, which means that the ID after the shift, the ID becomes the top of the stack, and then at the input I have plus number times ID. Okay, so I consumed this ID. Now I look at the rules. Is there a rule that ends with an ID?
Yes.
Yeah. So rule number 8. So rule number 8 ends with an ID. So in this case, and the the look ahead is plus. To validate this choice, does plus belong to the follow set of factor? It does not belong to the follow set of factor. So the factor cannot have a plus after it? It can. Because the factor is, can be the last thing in a term, right? And the term can have, the term can be, can have a plus after it because it's, the term can be the last thing in an expression. And an expression can be followed by a plus or a minus, right? So so the plus belongs to the follow of factor. So this is a valid choice. So I just reduce by rule number 8 by 8, and reducing by 8 is going to give me this becomes a factor, and this stays the same times ID. I think I will need more space, so I think I will need more entries.
These factors.
Okay. So now, what's the action? So I look at the top of the stack, the factor. Is there a rule that ends with a factor? Number 6. Number 6 ends with a factor. Well, now, number 4 and 5, they end with a factor. But I don't have this on the stack. So I'm looking at the left context. My left context has only factor. So term divided by factor and term multiplied by factor are not options because I don't have them. I don't have them here. All what I have is a factor. So this is rule number 6 is the only possible reduction. So I reduce by 6. Or just let's call it reduce 6. Okay. So by making this reduction, the factor becomes what?
Term.
Becomes a term. And I still have plus number times ID. Now, is there a rule that ends with a term? Yeah, so rule 3 ends with a term, and plus is a valid follower of expression, right? So I can reduce by rule number 3. Of course, I have these rules, but I don't have expression plus term or expression minus term. So all what I have here is a term. Okay, so I reduce by 3. Reducing by 3 reduces the term into what? An expression. So now my term is an expression, and I still have plus number times ID. Okay. Do I have a rule that ends with expression? Yes, I do. This ends with an expression. So can I substitute? Can I reduce expression to goal?
The follow doesn't include plus.
Yeah, exactly. A goal cannot be followed by a plus. The goal is the sole start variable. And when you have a sole start variable, the only follow is what? End of file. So what I'm seeing here is not end of file. So right now, even though expression appears on the right-hand side of one of the rules, it's not a valid reduction at this point, given the look ahead. So the look ahead told me that you have a plus coming. This substitution is valid only if what I'm seeing in the input is the end of file. Okay, so I'm not gonna reduce. When I don't reduce, what do I do?
Shift.
I shift. So when I shift, I have what? Now I have expression plus. So now this is the top of the stack. expression plus, and now I have number times ID. Now what should I do? Do I have a rule that ends with a plus? Because I'm trying to, match this, the top of the stack. I'm trying to match it with the right-hand side of one of these rules. So I have to find a rule that ends with a plus, not contains plus, because I want to, substitute something for this. So I have to find something that ends with a plus. This does not end with a plus. This is not a good match because the plus does not appear at the end of the right-hand side. So this does not match yet. So I don't have any match. I don't have anything that ends with a plus. So I can't reduce, then I shift. And when I shift, I consume one more symbol. So I have now expression plus number. And now the number disappears, and I have multiply ID. OK. Now, do I have a rule that ends with a number?
Yeah.
There is only this. So I just substitute factor for reduce number to a factor. So I reduce what? Reduce by rule number 7. Yeah. I reduce by rule number 7. So I have expression plus factor. And I still have multiply ID. And OK. So now I have a factor on the right-hand side. So do I have a rule that ends with a factor?
Yeah.
So this ends with a factor. And is this consistent with the look ahead?
No.
Can a factor have a multiply after? So think about an actual,
Yes.
well, 5 is a factor, right? 5 is a factor, and it has a multiply after it. So a factor can have a multiply in its follow set. So we're not showing the follow sets explicitly because they should be obvious for the most part. So factor can be, I can reduce factor to a term by rule number 6. So I have expression plus term, and this is ID. OK. So now expression plus term, should I substitute
Rule 1.
Rule 1.
Rule number 1, which is expression plus term? But does the multiply appear as a follow for expression? So expression can be followed by, expression is basically your start variable. So it can be followed by end of file or close parentheses. Yeah. So it can be followed by end of file or close parentheses. So it's not. I cannot substitute. I cannot substitute expression for, well, in fact, I have expression plus term and I have term. So both of these are valid because I can choose to substitute expression for this term by itself or substitute expression for the whole thing. And in fact, in both cases, I will end up with an expression, but an expression cannot be followed by a multiply. So I cannot do a reduction that will make an expression appear here on the stack based on the follow. So now, if I can't reduce, then I shift. And when I shift, I will have expression plus term, what? Times. And then I only have ID. Do I have a rule that ends with times?
No?
No, then I shift. Okay, so now I shift again, so I get expression plus term times ID. So in fact, what I have now in the input is end of file. I should have shown end of file after all of these, each one of these. Now, the ID can be replaced with, I can reduce ID to a factor. So I reduce by no more shifting is possible now. Now I reduce ID to a factor by 8. So I get expression plus term times factor. Okay. And now I have factor Now I have factor, and I can substitute terms times factor, right? Terms times factor, or I can substitute term for factor. Now this is here. It's not obvious. It's not. I don't have an obvious way of telling which of these two possible substitutions, this or this. Yeah.
Right, but with your left context, you don't ever have a place where there's a multiplication sign to the left of term, right?
Okay, a multiplication sign to the
left of term, so you wouldn't be able to do just factor.
Okay, yeah. So it's this is not based on the follow set. So you are reasoning about the left context, and this is correct, but it's we need a way of doing this systematically. So you are right, but well, how does this translate into a systematic rule? In fact, we have not yet described how we can systematically decide when to shift and when to reduce and which rule to use for the reduction. So we have not yet described this. We're only trying to understand how this bottom-up parsing works. So here let's put just a question mark, and let's say with some magic or logic maybe, with some logic we can determine that term times factor is the right reduction. So this question mark indicates that it's not quite obvious how we can systematically decide which one of these two possible reductions is the one that we should take. So now let's this is going to be the right one. So we will do this reduction. Now we will reduce term times factor with term. So we're going to reduce by rule number 4, and reducing by rule number 4, we will get expression expression plus term, and we have end of file, of course, end of file. Now again we have term, and we have expression plus term, and it's not clear how we can systematically. Of course, in this particular example, it's clear that expression plus term is the right reduction, but this question mark here is there because it's not clear how we can do this systematically. How we can do this? How we can come up with a general algorithm that will always tell us which rule to use for the reduction. Okay, so in this case, we reduce by expression plus term, we reduce by 1. And reducing by 1 will give us an expression. And now we only have one option. There is only one rule that ends with expression, which is expression goes to goal. So now we reduce by 0, by rule number 0. And reducing by rule number 0, we get a goal. So if we got our start variable, then this is the end of the derivation, and this is successful derivation. So in fact, this doesn't show it shows how bottom-up parsing works, but it doesn't give us a systematic approach for determining whether to shift or to reduce. And in case of reduction, which rule to use for reduction. This is exactly what the Lr1 parsing algorithm is about. It's about a systematic way of doing this. And how does it do this systematically? It does this systematically by basically tracking as we are parsing the input, and as we are processing the symbols in the input string, it keeps track of where we are in each rule. So it will have a placeholder in each rule. In this case, the placeholder, for example, will start here. So in the beginning, before we start parsing, our placeholder is here. But since our expression, the first rule will have an expression, then we are also here in this rule. This is what we call implication. This implies that if we are at the beginning of an expression, then we are at the beginning of a rule that defines expression. And the rule that defines expression is this rule. So we are at the beginning of an expression. This is what we have initially. We are at the beginning of this. But again, we are here at the beginning of a term. So in fact, we are at the beginning of any rule that defines term. And there are 3 rules that define term. But this also implies that initially we are at the beginning of a rule that defines factor. So it's going to imply that we are here, here, and here. So this placeholder, and you'll see lots of these placeholders in the next couple of lectures. These placeholders track our progress, where we are in each rule. So basically, for each rule in the grammar, there is a placeholder that marks where we are for this particular rule, given what we have parsed and what we have reduced, what we have done, and given the look ahead. So we're looking at both the left context, what we have done, and the look ahead, which is the symbol to be read next or to be consumed next. And based on that, we keep these placeholders. Now, applying Lr1 parsing to this big grammar is not going to fit on the board. So it's going to involve a lot of processing and a lot of bookkeeping. So we will do a much simpler example. And this simple example is goal is A, and A is A, or A. So this is the example. This is an easy example. Let's get started on this. We will not finish it today, but let's see how far we can go with this. So this is our example. Goal is A, or let's write it this way, or A, so that we can number the rules. So this is rule number 0, rule number 1, and this is rule number 2. So basically, this is the simplest example that we can have to show how Lr1 parsing does this, marking of the progress within each rule. So Lr1 parsing is going to say, okay, our initial state, state 0, or let's put it here. State 0 is going to be this state. We are goal A, and we are at the beginning of A, but we should keep in mind that our look ahead is end of file. What does this mean? It means that when this dot moves from goal to the end of A, this placeholder moves, then we should see end of file. Okay. But now, since we are at the beginning of A, we're trying to track our progress in all rules. So we are at the beginning of A, so we look at all the rules that define A, and we put a placeholder at the beginning of each one of them. And here we have two of them. We have this A is A. Now, what's going to be our look ahead? Our look ahead in this case is going to be the end of file itself. And here, A is A, and we are in the beginning of this, and our look ahead is end of file itself. Now, this is interesting. We continue these implications. So this rule, the main rule, implied these, because if we are at the beginning of A, then we are at the beginning of all the rules that define A, and we put the two rules that define A. But then we will have other implications. In this case, we are at the beginning of an A, but we should have a rule, we should be at the beginning of a rule that defines A, but in that case, our look ahead should be what?
Little a.
Should be little a. So this will imply A, the beginning of A, but with a look ahead of A, and all the rules that define A, including this, with a look ahead of A. Now, I guess this is probably the least intuitive part of Lr1 parsing. I think we are out. No, I think we have a minute. So let me say something about this. Then we will discuss this in detail next time. The least intuitive, or at least this is the part that students find the most difficult part of Lr1 parsing. Students usually have a hard time understanding why we are doing this. So we are at the beginning of this. This implies that we are at the beginning of any rule that defines A, but implication doesn't stop there, because this implies that we are at the beginning of a rule that defines A, but in that rule, an A is followed by a little a, not by an end of file.